Howdy, everybody. Hope you're doing well wherever, whenever you are. Thanks for joining me in this timeline in the multiverse. I thought today was another fun day. I don't think it was too hard of a problem. I imagine the brute force solution is probably a little bit harder. Like if you just take the naive approach of using part 1 for part 2, but times 12, right? Maybe it's a little bit harder. But if you've heard of like greedy algorithms before, sliding windows or two pointers, I don't think this day was particularly tough. Maybe I think for me, I just had a couple things that I had to like I had to think about, like, oh, am I pulling the right segments and stuff like that. So anyway, I'll show you my solutions. It's quite possible that there's a whole bunch of different ones. We'll look and see what we got, but I think it was a fun day. Had a lot of fun. Got some comments. I did look at the leaderboard, and I'm totally getting owned by, you all. So that's not be unexpected. So, but it's a lot of fun doing this and doing it kind of competitive. It'd be nice if we could get more details about the leaderboards, like. I did like that everybody codes, even though they had like a global time. They did have like a local time. Like, when was the first time you opened up the puzzle while you were logged in, I think is the way it works, I presume. Or like you made an API call to get your info. Anyway, that was a lot of fun. So I don't think I'll ever be able to do Advent to code like competitive like the day of. I'm always going to be a day behind, like I had mentioned. But that being said, it's still a lot of fun to solve the puzzles, and I would like to get better and faster. I feel like as I'm getting older, my mind takes a little bit longer to solve these problems, and so doing them regularly, I think, has helped me a lot. I definitely feel like I'm getting faster, so that's good. So anyway, let's get on with the day. I love all your comments, love all your thoughts, love reading through your stuff. Here we go. So this one's another elevator problem. There always seems to be a problem with the elevators in Advent of Code. Either they're not working, or you can only use them certain ways, or things like that. So, but it allows for us to solve some puzzles. So, but if I were Santa, I'd be looking for another elevator maker. Anyway, the elevators aren't working as you're trying to like go up to do the decorating. We're 3 days in and you have not done one bit of decorating, so that's not good either. But they say, oh, what we can do is we have some batteries that we can give some emergency supply to the escalator. Wait, I thought it was an elevator. Oh, we are working on the escalator now. The elevators are just gone. We're doing it with an escalator, but we gotta jolt the escalator to get it to work using some joltage, which is from a previous year. Anyway, the idea is you have this like bank of numbers for each battery, and so this is the joltage for each battery, and you want to know like what the two largest what the two largest values from left to right are within this, so that you can like connect those two values to the escalator to get it going. I think that's the gist of what you're trying to do. That the algorithm itself, if like you remove the story, is can you find the largest two digit number from a string? And like, so what it's the way that it shows it is like, okay, well, clearly 98 is the largest here, so 98 is the largest here. And if you think about it intuitively, obviously a 9 would produce the largest number unless it was at the end, right? So but it might be the largest right hand number. Like, I think maybe the thing to think about is like, you have two digits, how do I maximize these two digits? And the left hand side is going to be the highest digit you see up until this point, and then up until this point, and then the right hand side is going to be the largest digit to this side of it, right? To the other side. So you're kind of doing what I would describe as a sliding window. I realize I think it's technically called a two-pointer in this one. So if we're all being pedantic, I think it's technically called a two-pointer because the left, oftentimes the well, I don't know, maybe it works, but I've always considered a sliding window anytime where you have like two pointers and you're like growing or shrinking it. But I think the general gist of all of those, they're called two pointers. And so this is definitely a two pointer. And it's possible that a sliding window is like a specific window size that just goes across. So anyway, regardless, I think I named it two pointers because I don't. In previous videos, I may have called it a sliding window when it maybe technically wasn't. I guess we can look it up, or someone can look it up and tell me whether I'm right or wrong. There'll be some great reading before I fall asleep. But the gist is you want to like find the two largest numbers. And so in this case, obviously 8, 9. Here is 7, 8. Here is 9, 2. I think the way to think about it is if you ever see a 9, that's probably going to be the largest left. And think about this intuitively. If there was ever a 9 anywhere, even right here, it would necessarily be larger than the 8. Does that make sense? Like the biggest 8, the 8 could be is 89, but the 9 here could be a 91. So you're always going to be kind of going from left to right. And so in your two pointer system, you're going to have like a left hand side and a right hand side. Sorry, like I'm drawing very well lately. And the left is the largest digit seen, and the right is going to be the largest since index of left. So you can imagine like if you had so again like the number I don't know 2, 3, 9, 5, 6, 4. You're going to have like a left pointer that's going to point here and a right pointer that's going to point here. And it's going to start looking like this. So right now our current largest number is 23, right? But now when we inspect the 3, we're going to say, oh, the 3 is larger than the 2. So I'm actually going to move them now. And so I'm going to make, maybe I'll just stick with green. I'm going to make the 3 here, and now this will now be the new one. And so now I'll check this range right here. Oh, 39. So now 39 is the largest. Right? So now, but I say, oh, but the 9 is larger. So I think I actually need to move these now. So I'm going to make it this. And now is 95 larger? Yes, it is. So my new high is 95. Now I'm going to, 5 is not greater than 9 though. So I'm going to keep the 9 here. And in fact, now that I've hit a 9, it will stay there forever. But following the algorithm, we now look for the next one right here. A 6 is larger. So we get 96 is now our new largest. And then we move it one last time here to the 4. The 4 is not larger, so we maintain 96. We've reached the end of the array and we're done. So we know 96 is the largest number. That's just what we're doing. So it's a two-pointer system where the left is like the start and the right is like you're like iterating through the rest of it. This is an ON operation, right? So this is ON. And so you're only going through it once. So I don't imagine you could come up with a faster algorithm. This is what I'm saying. It's directly linked to the size of the input, and the inputs here are relatively large. I think I counted them at 100. So there are 100. I did not count it, by the way. I did a stir lane. So how do we solve this? Part 1 then? Next, part 1. Here's my code. first we need to parse these. Again, I'm kind of having fun returning an iterator. I don't know that it's faster or better, but so I'm sticking with it for a little while. You'll have to tell me what you think about it. Maybe you or don't like it. How do we parse? We turn each of the we just take each line and we turn it into the we iterate over the characters of that line. We turn each one into a digit and map it as a U size. I think 2-digit returns a U32. Yeah. So this one, because we know it's a digit, I probably could have used a U32 safely. Anyway, so this is going to give us a vec of U size. So each line in our input is going to be a vec of U size that we're going to. And then here's our 2-pointer solution, right? So we say, give me the bank. And I used a scan here. So if you remember from last time, the scan is like fold, but it's going to return a value each time through. And that's because I can use my left-right pointers. So this looks a little different than the left-right pointers that you might be a loop that you're probably more familiar with you'd have L equals 0 and R equals 1, and then you'd have like a while R less than len, the length of the array. And then in here you do your logic, right? There's some logic in here, and maybe you have like an if something, if R greater than L. It should be like, I guess, B R greater than L. This is where you'd say L equals R. Here. Sorry, this is not great. You could do it in a while loop, I guess is what I'm saying. I chose to do a scan. So we start with our left being the first value, and then we're going to scan through the rest of the values. So my pointer thing is, I'm technically using a pointer, but I'm using the actual value, I guess. Or I guess not technically, I should say. Generally, I'm still using the 2-pointer algorithm. But the value that my accumulator, the value that I'm tracking is what my left position is. And then my right is always the next value, right? The value in the list as we're iterating through the array. So I start with this being the 0 value, and then I iterate over all of the others. So I now have my left digit and my right digit, and I know my current value is now left times 10 plus right, right? So this is just to give me the actual integer value of the 2 digits. And finish this off, right? If right is bigger, right? So if right is bigger, we find a new left, and then otherwise we just return our current value, right? This new value. So the scan is always going to return our current biggest value or our current value of our thing, and then we just get the max of that one, right? So it's going to spit out all the values, and we're going to track what we're going to say, what is the max. Again, if you were doing this in a loop, you'd have like largest equals largest dot max per or whatever the current value is. You'd be doing that. Because I'm able to scan, I can just do max. So it's gonna spit out the way to think about it is what this is going to spit out is it's going to spit out these values right here. So it's going to say 23, 39, 95, 96, right? 23, 39, 95, 96, and then 94. It'll also spit out 94. Draw that right, but so it'll give you 96. Okay. So this is me using scan to implement the 2-pointer system. I suppose I could show you how to do maybe this will make more sense if we do left 0. Be something like this, right? Well, less than bank lane, largest of left bank, left in, right. Um, left, right. Largest. Return the largest. Wah, wah. Nope, now we're failing. Okay, so what am I missing? Well, right, less than bank, left, right. Largest, largest max. Bank left times 10 plus bank right. If bank right, left. Oh, that probably, there you go. Yeah, you want to start left at the first point, the first value, and right at the second. Obviously, this assumes there too if you're doing some special checking. So this is more traditional of what you'd see in like a non-functional style solution, right? You have your left and your right, and then the largest value that you've seen, and then you say, while I'm not at the end, while the right is not at the end, I'm going to say, update my largest value based on what my current one is. And then I say, if I ever find a larger one, now update my left to be that value. But I'm always incrementing the right value. I always go, right always keeps going up. So I'll leave this in here. Maybe it'll be easier for you to grok that one. I don't know. Sometimes the functionals don't seem like they're super easy to read, understand. But there you go. Okay, and that's part 1. It's not too hard. 2-pointer system. Okay, part 2, I think can be deceptively hard, but if you think about it intuitively, is actually not as hard as you think it is. Where I think you'll run into struggle is if you're not used to like recursion or what's known as a greedy algorithm. Like those are the things that I could see like being an issue. So what do they say in part 2? They say, okay, well, now you've tested it with like 2 digits, but I want you to test it with 12 digits now. And this, again, this number is misleading right here because there's only like, I don't know, 15 digits here or something. So you're going to use most of them. And if you were looking at the image, you say, oh, I'm just gonna take all the numbers and delete the 3 smallest from right to left. Find the small. Which I guess is still a greedy-ish algorithm. I'll show you how I solved it though, and you can look at it. But the idea is, well, you now have 12. You now have to pick 12 digits instead of 2. So can you really keep 12 pointers? I mean, potentially, but it feels a little bit more complex. Probably what's easier, and how I solved it, I'll show you. Sorry, my thing keeps beeping. I don't. Hopefully, you're not hearing that. The way to think about it is, and it might be easier to see here. If you're going to have 12 values, like say that's 12. I don't know if this is actually. Say this is like the 12 digits right here. This is maximum of 12. Then you kind of want to pick the largest number among these digits right here. And not only that, but you want to pick the largest, the one that's furthest to the left, right? So if I'm just scanning right now, it's like clearly this 7 is the largest. So you'd want to use the 7 as that number, and then the rest of them you just say, okay, we'll find the largest for the rest of them, right? So Yeah, so there's not a lot more, right? But so now you'd ask yourself, well, what's the largest from like this group? And but you can't go too far, right? Because you know you need to now accumulate 11 more. So I can't skip to the 5. So I may only be able to pick between these two numbers. And so I'll say, okay, well, I'll do the 7, and then I'll do between these two I can pick the 2. Between these two I can pick the 3. So now I've got 7, 2, 3, and now I don't have any more space, so I have to pick these exact digits. So that is the largest number in that thing, right? And that number is going to necessarily be larger than any other number on the left side, because there's no other number that's larger than a 7. So that is to say, you couldn't use the 6 here to find a larger number, because even if there's a bunch of really large numbers here, obviously the first number is a 6, so it's not the largest. So the intuition behind that should like be saying, okay, well, I really just I need to find some subset of like allowable values and find the largest there, and then try and find the largest with the rest of the values that I have left over. And this is called a greedy algorithm. And we could talk about greedy algorithms if you're interested more. Um, but the idea is a greedy algorithm is just like, given a subset of the problem, find the best value that you can, and then do that for the rest of the subset. So it is recursive in nature, or in that sense that you're saying you're doing dynamic programming in that sense, where you're saying find the best in this subset, and then with the rest that I have left, find the best, and then with the rest, find the best, and we're going to do that in this case 12 times. So just to reiterate like how that works is, and I won't go through all the numbers, but imagine you've got some list this, like, that's this big, we'll say, and like 0, and this is 100 or whatever. When you're trying to solve this problem, you want to ask yourself, well, how many do I have left? We're going to start at 12 left, right? So we know we can't pull any numbers from any over here. Well, let's, instead of using 12, let's use 10. We know we can't pull from these last numbers, right? So we know the maximum we can pull from here is from like 0 to what is it, 90? Something like that. It's probably 89, I guess, because if I ever use the 91st one, I won't have enough to use the rest, right? So what I want to do is say, hey, from this block, what is the best number? And maybe it turns out there's a 9 right here, right? There's a 9 right here, so I know I want to use this one. Okay, so I know now I have a 9 is in my list. And so now I want to ask myself, given that now that this position of the 9, can I find that I now have 9 numbers I need to fill. So I want to find the 9 largest in this new block, the way I can describe it now. So I have a new block now that's from here to here. And so it's going to say, okay, now can you find the 9 largest from this block? And so I can now go one more, right? I can go to like 91, right? And so yeah, so actually the block now goes to like right here, right? So I can now go to 91. So I want to find the largest number here, and maybe it's right here. It's a 6 or whatever, right? So I now know with 9 left, I can do a 9 and then a 6. And I'm going to do this one more time, and then we'll be done with this explanation. But so one more time, now I know like from this index to here, I want to find 8 more larger numbers, right? So I'm going to say, okay, now I want to do it for 8, and I know 8 starts right here, right? And it goes to right here at 92. And so I want to say, what is the largest number I can do here? And maybe it's a 4 that's right here, right? So I now know that I have 9, 6, and 4. And you're just going to keep doing this on and on and on until you find like the largest subset from that thing. And it's recursive in nature. Again, if you're new to recursion, it can seem a little complicated. It can feel like magic, and I've said that a lot of times. It's because it kind of is magic, right? The idea that you can break a big problem into a small problem and just solve that small problem over and over again is really cool. The things that you just have to figure out is, well, what is the subset of the problem that I want to solve for this like specific problem? And sometimes that can be tough to like figure that out and reason about it, but it comes with practice, I promise. So if it doesn't make sense, keep practicing it, keep trying it. Anyway, so here's the solution to the quote unquote greedy algorithm. We're gonna be given a bank size. Like, here's the size of our bank, and this is actually the bank that we have left. So it starts out being the whole bank, but as we find numbers, it will be like recursively smaller, right? It'll be smaller. How many more digits we have to find, and what our current total is. Okay, so those are the three things we need in our greedy algorithm. We need to know like the bank of values that we have left, how many more values we need to select from that bank, and what our current total is, because that will help inform us what the overall total is when we're done. And in fact, that's the first check we do. This is like the sentinel check or the base case. If the remaining is ever 0, then we're done, right? We've picked all the numbers. There's no numbers left to pick. And so we're going to pick the large, and so we now know the total we have is what we wanted. Otherwise, we want to find the largest value we can find within the bank that we have left. And remember, I said we have to kind of like cut it off. So here's me cutting it off. I'm creating a slice in Rust. But we say, okay, I'm going to cut it off. I'm going to start at my bank lane, but go to minus remaining plus 1. And this has the effect of this part right here, right? Is like finding this value right here. Meaning I know I can never go past these values right here because I would not have enough digits remaining to like go past them if I did. So in Rust, we can just iterate over this slice. We enumerate because we want to find the position and the value. We'll use that next, right? And then we just want to find the max value in that chunk that we have, that current segment, that subset that we have right now. And the way you do that is you do a rev max by key, or at least it's the way I did it, right? You want to find the largest value in this thing. Max by key returns the last largest value. So if you're iterating through like the orange block again, say we're iterating through this orange block, if there's a 4 right here, max by key would return this index. It would return the number 4, but it would also return this index, right? So, well, I guess it returns what you tell it to return, but it's always going to return that position. The max by key is going to return that position. It's going to return the last one that it found. And so in order to find the smallest one, we want to do a rev, right? This doesn't change the speed of anything by reversing it or doing max by key. Because we're looking for the largest value, we must necessarily find the largest within the whole set, which means we need to evaluate each value in the set. And so we're just going to do it in reverse and call max by key. And this helps us ensure that we get like the first 4, right? Like, think about it from this perspective. If there's 2 4s in here, we always want to pick this one because it gives the rest of the values the more of this space to pick the largest number. If we pick this one, like maybe there's I don't know, like a 3 right here, and the rest of these are 1s, right? We'd want to be able to put that 3 in front of the rest of the 1. And so that's the reason we do this. We just, again, we enumerate, or I should say we iter through the bank that's available to us, like the sub slice that's available to us. We enumerate so we can get its ID, and then we reverse and max by key to get the first max value. Now, once we've done that, we just call recursively. So we want to use the, obviously we've used up the bank this way. So we don't, well, I guess it's the other way for you guys. We've used up the bank this way. And so we don't want to use any more of that, right? So we're going to return, or we're going to call it on the slice from here to the rest, to the end of the value. And we're going to decrement our remaining because we've now found the largest in that value. And we're going to decrement that, and then we're just going to return the total times the largest, 10 pow remaining minus 1. So this is just shifting that largest digit correctly to where it will be in the final position, right? So if we know the 9 is in the first position, we want to times it by 10 to the 12, right? And that will have the effect of, I guess, 10 to the 11. That will have the effect of moving it all the way over. And that's it. That's the greedy algorithm, right? So I hope that makes sense. It turns out to be like only 3 lines of code or whatever. I don't know how you describe this, where you just say, oh, if I'm ever done, like I've found all the values, I just return my total. Otherwise, I find the largest for this segment that I'm allowed to find. And then I call that recursively with the rest of the string after the largest value, and then my remaining is minus 1, and then I update my total so that when we're done, I get the actual total. This algorithm is I don't think you can get any faster. It's O of nk, probably. Technically, this is a constant, so it is O of n. And you can see that kind of bears out in the solution space, right? It solves really fast. I think technically it's O of n. Like if you were to like go to a computer scientist and say, what is this? It is technically an O of n solution. I think more people would be inclined to use this right here, though, to infer that for especially large values, this takes longer. And why do we put this n of k here? Like, think about what you're doing each time. Is for this segment you have to iterate over those values, and then for this segment you have to iterate over those values. And so in this case, k is 12, right? Each of these are going, how do I say this? Each of the values in the array, we're going to consult about 12 times. It's actually not 12 if you think about the way the logic works. Is like these initial values are only consulted once, but like these ones are consulted like, I don't know. Well, actually, these ones are consulted very little too. They're only consulted, about half n over or k over 2 or something like that, half as much. But like these middle values are actually consulted quite a bit. And what do I mean by that is like some value here is going to be used for, a lot, potentially used for a lot of these. And so a lot of people will say k to kind of give you the idea of like, it's not strictly O of n, meaning you just, the original solution or part 1 is definitely O of n, right? Because you're only ever consulting each value essentially once, right? Each value is only getting like evaluated once. Whereas this one may get evaluated multiple times. But again, it's still an extremely efficient solution either way. This k is like 12 in this case, which technically means it's O of n. But it's not exactly O of n, but you can still see it solves absurdly fast. And this would still solve absurdly fast even for extremely large. Like if you made it, instead of 12 it was 50, and instead of the thing it was like a billion, or not a billion, but like 1,000 digits that you needed to consult, or even 10,000, it would still be an efficient solution, and probably the most efficient solution, at least as far as I know. So we'll look and see if I'm wrong. But in my analysis, I was like, oh, surely this can't get much faster than this. I think the way you'd optimize this is not via the algorithm, but like how are you using the values, how are you parsing and indexing and things like that. So anyway, that was part 2. I don't think it was too we're only 3 days in. So the I think a greedy algorithm, if you used it before, probably not too tough of a problem. I imagine I would be surprised if there was another solution, but I've been surprised before. So, let's find out. Let's go look and see how everyone did. Let's see. Brute forcing. You could not live without your own failure. Where did that back? All years, all days, it's inevitable. Could you brute force this? Probably. Because there's only 100. I mean, 100 times 100 is like what, 100,000? Like okay. So what is the brute force solution? The brute force solution is you take this value, and then you say for each of these, give me the 12 largest or whatever. So like, say it's 100 times 100. Actually, it might be 100 to the 12, which may not be brute forceable. I think it's 100 to the 12. So it may not actually be brute forceable. If you brute force it, I'd love to see your solution. Last year I did off. Imagine having to do when someone interrupts your advent of code and asks you to actually do something for work. Okay, it is. I do the. This is fair. When I'm in a boring meeting that I don't want to be a part of, that I have to go to because someone said I have to go to it, I do my advent of code, and then they're like, "Josh, what do you think about that?" And I'm like, "Oh, yeah, that's great." So that does happen. Terminal visualization. Yeah. Okay. This is it. It's still this little visualization is essentially using the greedy algorithm, like I was mentioning. It is still just like stepping through it though. Like it's saying, okay, what's the largest here? It has to be doing some additional checks, right? Uh, but like once you find a larger value, you definitely want to reduce it. And at some point, you say, oh, I can't get any larger than this, and so you're done. Oh, now I've been. Oh, Easter eggs. Okay. Yeah, I don't usually find the Easter eggs, but they do show up. I love brute force. Oh no. Yeah, you probably couldn't brute force it. Day 3 to a question. Escalator can never break. It can only become oh, this I do love this joke. This is funny. You would never see an escalator temporarily out of order sign, just escalator temporary stairs. Sorry for the. There's a little joke going around because the escalator broke. Uh, for the president in my timeline, and it kind of became funny for a while. But it reminded me of this joke, and I went back and found it. And here it is again, the escalator. It can never break. It only becomes stairs. A linear time algorithm for both. What was your linear time? Mine was closer to the number of batteries. Closer to NK is arbitrary. A solution works first attempt. It usually takes me like 3. That's cool. Yeah, recursive solutions can be kind of confusing because you have to think about like what is your subset and how are you solving for that subset. So that's cool that they got it the first time. It's really easy. Just look for the largest for the last -11. Then if that was the x, look for x plus 10 and so on and so forth. That's essentially what I did. K is a parameter, no K is a constant. It's always 12. Yeah, these guys are kind of fighting over semantics. Here's a great way to start a war. Talk about big O notation, apparently. I think permits, I think they're both right to some degree. They're talking about two different things. K is a parameter, not a constant. I mean, in this case, it is a constant. It is 12. Like, and that's the thing. Like, from Kebab My Bob point of view, like the generalized solution, the general solution, K is a parameter, and so it is K does affect the thing. But like, I mean, realistically speaking, if you're trying to solve this problem, you probably wouldn't use this solution in a general case. K is actually a constant, it's 12. So they're arguing from like two sides of the same point, and this is why I take the big O notation somewhat loosely. Here's what I'll say about this. If you can say it's O of n versus O of n cubed versus O of log n versus like O of 2 to the n, or O of n to the n, or something like these. Like, if you can generalize putting it in these categories, like, I think that's helpful, right? So if you're looking to like, can I figure this out? I think like these are the general categories you want to figure. Like, is it efficient? Like, I think like these three technically fall in the quote unquote efficient category. And like these ones definitely do not, right? Like, as n gets larger, these solutions just become impossible to solve, right? And there's other variations of all of these values, right? I just 5 random ones. You're generally looking for solutions that are like n or log n, or maybe more n log n, right? Like, these are, most sorting algorithms are like fit in this category. I mean, I shouldn't say most, but the more efficient ones kind of fit in this category. N cubed can feel like, oh wow, that's a lot, but it's actually not a lot, like compared to like these ones. Okay, I won't say much more about it because I would want to do like more reading to make sure I'm saying the exact thing correctly. But I think these two people are actually arguing points that are like, they're both like right for what the way they're thinking about it, but not quite right in like what's actually happening. There's kind of like arguing over these things, right? No, K is a constant. It's always 12. It does not. Yeah, I don't. I mean, I think these are both right to both of what they're saying. Then it's O and K, not O N. Might be 12 is negligible. It's factor the stack. This K is constant. K is not constant just because we know K here. Makes perfect sense to consider K as a parameter. See, I think they're arguing, is it a parameter here? Because the definition of the problem, K is constant, right? Like, that's what this argument is revolving around. Is K constant, or is K a parameter? In this solution, K is constant, right? We've read the problem. They've told us what K is. They've said K is 12. And so what they're saying is, solve this problem for K equals 12. So that's the thing. I think they're both arguing both sides. So I can see what permits is saying, but I can also see what these guys are saying, because if you're trying to find a generalized solution to a problem like this, that is, can you pick the largest set, or maybe just a greedy algorithm in general? a greedy algorithm in general would likely have an ONK solution to it. I even say that? I think I was saying that up here, right? Like it's like ONK right here. I think the generalized greedy solution is ONK. Because we know that it's only 12, it's kind of ON. So, okay. Monotonic stack is ON. All these people are going wild. I did found part two. This would be a good question to maybe ask. We actually try AI. We just see what Gemini says. Four, three. Oh, four, three. What is and oh, well, I bet if you ask this to different AIs, you'd get different solutions. Let's see what they say. We'll let it think while we go look at others. All in, off by one bug, for off by okay. This totally happens, right? Like if you look at my solution, these ones, I was like, I really had to think about this one and this one. You know, I'm like, ooh, where am I? And this one right here, I actually had to think about too, right? It's the bank minus the remaining plus one. And that was a little weird to me. And it was because you want to include like the remaining values. And so it's a really weird one. But it happens. I thought it through enough that I'm almost positive this is the right slice that you want to slice out of it. This one's kind of more obvious because obviously you don't want to use the value at the current position. You want to use like the rest of the values recursively. But you know, that this one right here really had me for a second, like thinking about it. As well as this one right here, like what am I raising this to the power of? It happens to be remaining minus one, I think. So, well, I think it's right. So that's because I got the right answer. So okay, here we go. What does it say? How you define the input size. Let's analyze the greedy function. Let m be the length of k be the number of digits to select, which is fixed at 12. The greedy function, recursively called k times, and each call it iterates over a slice. Worst case analysis. Okay, well, I'm not really interested in the worst case. K scans of m minus k was and k, m times k. Best case, oh, m. Since big O notation refers to the worst case, the strict answer for the given implementation is mk for a single line. O n and k. Their case consider variable constant. Arguments for a purely arithmetic algorithmic standpoint, if k were a parameter to the function, the complexity would be O and k. This is described how the algorithm runtime scales that both n and k can change. Hardcode constant. Both arguments have merit depending on the context. That's exactly what I said, right? It since k is fixed, it's a known constant, so it's O n over the solution. does it know I'm doing advent to code? Oh, maybe it's in my folder. It knew my folder. I was like, what do you know, AI? Didn't, well, I mean, knows a lot. Okay, where are the answers? I want to look at some of the answers. Let's see what we got here. Advent to code. Nope. Day 3 solutions. What is the C? I've looked at a couple C++. So admittedly, I haven't done C++ in like 15 or 20 years. And it does not look like the C++ I once used. Yeah, what is this? Do I need to take another C++ class? Cool. Mine uses D. Oh yeah, you can do func tools cache and memoize. My code for part 2, return max f sp s. I mean, I think this is a greedy solution. I don't think it's dynamic. I mean, it is dynamic programming. I get, generally speaking, we look this up. Dynamic programming is like the notion of like breaking the problem into small parts, right? So it is technically dynamic. It's just a specialized version of it called greedy. It was fun to treat all test cases at once. I actually, there aren't a lot of them, and so it didn't seem worthwhile. I actually think the parallelization would hinder this problem because the number of that you do is so small that setting up the parallel processing worse. Dialogue. I will not be able to figure out. Any golfers in chat? Took me like 2 hours to even understand how to solve part 2 in the first place. Wait, why is it a golf thing? Is there a golf reference? I started too late, too tired, we'll catch up. Okay, here's a Rust solution. Find largest by index. Oh, they're using a string? Oh, so they're just maintaining the strings? I mean, you do have to sum them up eventually, so you do have to turn them into a number. Find largest by index. Yeah, there you go. So yeah, okay. I mean, it's a greedy algorithm. Again, can I search within thing, like within this solution? Okay, let's go back and see. I don't feel like, well, maybe we can keep looking. I don't think you're going to get better than the greedy. I'm using a C this year to practice learn. Oh, stud. Oh, impressive. Uh-oh. ON versus ONK. We're back at it. Let's look. This is crazy. So you might ask yourself, why would you do no standard library? And if you're compiling to like um, maybe microcode or on to like something that will be put on silicone, you don't want obviously the standard library because you can't like for example allocate memory unless you create your own allocator over a fixed set of memory. And so like in embedded systems and stuff like that, uh you often use no standard library. So you have to implement things like this, like pre-computing powers of 10 for the first 12 values, which is not too hard, right? What am I using? Oh, well, I'm using standard library all over the place, right? Because I'm doing crazy functional style programming. That's kind of a fun idea, is like how far could you go without the standard library? Some things like the ability to use a hash map, like crazy, right? Uh, General solution with low complexity. Solve 2, map solve 12. Oh, that's an interesting thing, is you can actually solve part 1 by doing part 2. So like I use the 2-pointer here, but should we just double check? You could actually do greedy parts. But I gotta go to parse map thing, bro. This should solve it as well, right? Huh. Yeah, there you go. They're actually both this. Like if you think about it, they're both the same problem. For me, it was easier to think about part 2 as a 2-pointer one. But that is true. You can actually solve this the same way because you're just taking like a subset of it. Again, in this case, we're looking for the largest 2 values for part 1 and the largest 1 part 2. So anyway, that's a good thing to think about. You could actually do it in both ways. Okay, max counter bank. Common Lisp. Boy. I My first language in college was Lisp. Does that age me? Uh Sorry, it's probably hard for me to like read because I'm trying to read them and understand what they're doing. Sometimes though, this is really cool, right? Like doing this in like a Lisp thing. I mean, I realize you could do this everywhere else, right? Like we could do this in Rust. It just looks different. Maybe not as many parentheses, but like at the same time, I was thinking to myself, actually, probably not much different, right? We use a lot parentheses a lot. Like, yeah, but I think this is still like a greedy algorithm where you're still like picking the largest and getting and solving the rest. Okay, let's. Uh, I don't imagine like the top solvers would have issues with this one. Uh, Five minutes. Did brute force for Q1 and DP for part two? The idea, yeah. Let's see what the solution is. If I equals len line and 12 returns. Oh, this is like probably some like this is not the solution. Yeah. Okay. I don't think DP is this. This is an actual DP because you're tracking this values you've seen at size 2, 3, 4, and like slowly incrementing them is what looks like it's happening. Do I have that right? Yeah. Yeah. I think this is more of like a yeah. I had to think about this. Is this more DFS in nature? I think so. And that's DP as well, but like still very cool. Obviously faster than I ever got it. Uh, I don't know. I still feel like these comments right here saying, "Oh, I didn't consider DP. DP may have been better." I mean, I. What do you mean by dynamic programming? Like this DP is when I think when they're saying this DP right here, what they're referring to is like for competitive programming. DP means tracking uh tracking like smaller values. So like first you want to try and solve it for 3, and then you say like what's the best 3 from like these 3, and then you say okay, now what's the best 4 or 3 from these 4 or whatever, right? And then but now you may say like what's the best once you've solved the best 3 for these 4, you can then say like, what's the best four for these five or whatever, right? And you kind of work your way up the list. And so I think that's what they're talking about. And what happens is if you ever find like a larger one, you then go back to your list and say, okay, well, I found a larger number, I found a larger digit over here. How does that affect my solution space for here? So now I want to find like what's the largest from this space, and that you can consult some of the work you've done before, so you don't have to redo that work. Like I think technically this is like a DFS with pruning, right? Is what they call it in computer science. Is where like you're saying, I'm going to maintain some set of like known solutions that I've solved before, and then I'm going to figure out. I'm going to use that to help me prune my search space for searches that I've already done before. If that makes sense. I think that's what's happening here. In fact, it is, if you think about it. You call F here, and you're like, if F is less than 12, I'm going to call it recursively until I get to 12. So it's going to do this part until it gets to 12. So it's going to find its first one along the tree of the solution space. And then it's going to use that as like oh, here's my answer. And then it will slowly start working its way back up the tree, but like you'll be solving these pieces over and over, and because you've kept like a memoized version of it, you don't have to repeat those things. You can reuse that work, and eventually when you fall down this side of the tree, almost all of it will be done, and you instantly get to the best answer. So I think that's what this is, right? We can verify, I guess. Let's just see what it says. But very good solution, faster than I could. I don't think at 5 minutes I had even finished reading the first problem. So, it's kind of cool to see these people solve it. Right? It'd be nice if there were some other people. I look for. Oh, here's one of we see this person a lot. Yep, use a vec8 to keep track of the digits. 14 and 28. Like, I think that's within my range, probably, depending on how old our computers are. Find max joltage. For 2, find for 12. Batteries count. Value start, batteries lane, in lane minus. Yeah, so this is pretty close to my solution, right? It probably goes faster because you're just tracking the U8s. So I do a lot of string conversion and then turning that to a digit. Yeah, you're just finding the max digit in its position. So this is like, again, remember how I said like max by key requires you to do it reverse if you want to find the lowest? Because it's digit greater than max digit, like you don't have to do it in reverse, right? And so this is, if you're doing it without max by key, this is a cool way to do it, is you say, oh, I just want to check if it's greater than the max digit. Because if you've already found a 9, you don't want to look for another 9. Same for, or a 7, for example, right? You technically, oh, and it's actually right here. Now that I say that, I was gonna say technically, if you found a 9, you're done because there's no other bigger digit. So this helps. This helps like break the sequence, right? If you've ever found a 9, you know it's the largest. 10 times value plus. There you go. Perfect. Yeah. So this is my solution. Again, just written in like a different way. And as noted, you can actually solve it with both of them doing, the first one for 2 and the second one for 12. So very cool. Okay. Lots of great solutions. Have I talked about it ad nauseum? What should we say? You're absolutely right. Specifically, it's a top down DP with memoization. Okay, so I am wrong about the DFS with pruning, it sounds like. Top down with memo. The function is likely to reach the same state though different through. It uses DFS traversal, but it relies on memoization rather than pruning. Okay, so I may be using that wrong then. That's good to know. Like, I think I've said DFS with pruning before. It's definitely DFS. Yeah, so this is where I kind of thought it was pruning. The idea is like, oh, sorry, you probably can't see. The idea is like why would I call it pruning? Is because eventually you're going to like get to a point in your like solution space where you're like, oh, I've seen this exact one before. I don't have to do it again. And so it is memoization. I should probably be clear that that's what it is. Um, yeah, branch and bounding is what it's called. So I am probably using that incorrectly. Um, so that doesn't. Okay, so it is. If you're submitting this for a competitive problem, use the label memoized recursion or top down DP. If you remove the dictionary, it would become brute force DFS. It's just a DFS over the solution. DFS with memoization. Okay. Or DP. Top down DP. Memoized recursion. Okay. Those are good to know. I'll try and keep my terminology right. There's so many of these terminologies to get right. So okay, what a great day. I had a lot of fun. I learned a lot. It was good to look at the solutions, some of the memes, any other funny memes. If I missed a funny meme that you liked, please share it with me. Well, look at all this very cool solutions. So I'd love to see it. Show me what it is. Show me your solutions. It looks like I did see a couple of yours already. And obviously we saw some, speed solver solutions, which are very cool. The thing about that's cool, I think, about speed solvers is they obviously you need to know most of the algorithms, but if you actually can solve it one way and it's not like the quote unquote most optimal, you still can win, right? Like DP, if you are familiar with DP and you know you can solve with DP and it's going to solve in good time, how I how you get it done from it or to work. Would this actually work on day 3? Maybe this is not it. Okay, so you can do it for part 1 but not part 2. Okay, that makes sense. If you're doing combinations for 2 parts, that's not too bad. But for 12, that's why I said I actually don't think you can brute force this, because I think it's 100 to the 12 seems large. 10 to the 120, right? Anyway, there you go. Good day. So again, send me your solutions. I'll put mine down in the down in the description. If you'd like me to review your code, send it. I'd love to see it. Again, it helps me. That's why I love reading through Reddit and that stuff. I guess I deleted Reddit. I love because it helps me learn and get better. So keep sending them my way, and we'll talk to you next time. Bye, everybody.